Hi, I'm Dave Baring, Technical Director here at TriStar, and welcome to another Tech Talk. This video is going to be a little bit different from the other ones because I want to address a topic that comes up quite frequently here at TriStar in our engineering department, and that is what I am going to call, what about those numbers? And what I'm talking about is the physical property data sheets that are out there on the internet, available from different sources and different manufacturers. And it can be a little bit overwhelming sometimes when you start to look for a particular material. And what I want to talk about is the things that you need to be aware of and some warnings as to what the data really means. So I thought to start with, I wanted to talk a little bit about not only the materials but the processes. And I've got a very good example of what I mean by this. We had a customer several years ago that went on the internet, went to a source that they had used before to get their data, and based their design around the data from this particular website. That's all good, except that what the customer did not take into consideration was what is the process that's being used to make that material. Most of the data sheets that you see out there in the marketplace are based on the resin suppliers' information, which is a little bit dicey because you don't know how they're going to process it. And to give you an example of what that means, I've got this little chart here that shows an example of the material that this particular customer was working with, and ultimately a very small error caused a very large problem and a failure in the field. Let's take a look at some of these numbers, and you'll get an idea of what I'm talking about. There's two materials here: unfilled PEEK, which is polyether ether ketone, and then a 30% glass-filled PEEK. And the thing I want you to notice is that there are three different manufacturing processes that are mentioned here: extruded, compression molded, and injection molded. With the glass-filled PEEK, I added a second injection molding source because I wanted to demonstrate that even the different processors can come up with different numbers. So let's take a look at the unfilled PEEK. Specific gravities are always going to be pretty much the same. Processing doesn't really change that. But if you look at the tensile strength, tensile modulus, the big one here is elongation. You go from 1 to 35. Flex is about the same, flex strength is about the same. You get some variables in shear, some variables in compressive modulus, some variables in hardness. Izod impact's about the same. Your friction and thermal properties are going to be the same pretty much no matter what process is used. But my point here is that if you don't pay attention to the process that's being used, you could get yourself in trouble. Now, these seem like minor differences, but the fact of the matter is a very minor difference could make a really big difference in the practical application. So the main point I want to make is that be sure that you not only compare the data on the material in terms of its mechanical data, the thermal properties, the electrical properties, and if it's a bearing application, of course, you want to look at the tribological properties, so friction and wear. At the end of the day, really what you're trying to do here is identify a material that you can start with, and then you're going to have to go through the process of testing. There's very few manufacturers in the plastics industry that don't have some form of disclaimer stating this information is based on the best values that we have, but it's up to you to test it for your actual application. So, as I've mentioned in other videos before, be sure that when you're talking about comparing numbers, that you're comparing numbers for the sake of looking at material A, B, C, and seeing which one of those materials is suitable for your application. Then you have to go to the next step, and that's to determine which process is the most appropriate for your application. And are the physicals and thermals and electricals going to match up with what you need? Most people will tell you in the plastics world that injection molded parts are generally going to have the best properties right down the line. So if your application is for thousands of parts and you can justify the cost of a tool, then it makes sense to go injection molding, and you're going to have the best possible result. But if you're talking about making 50 parts a year or even 500 parts a year, now you have to take into consideration the process. Is it going to be compression molded, or is it going to be extruded? Extruded material is the most common standard shape material that we use to make parts, but then you have to think about the size of the part. Is it suitable for the stock shapes that are available out there? There are restrictions. Some materials you can only make 2-inch diameter rod, some 4-inch, some 8-inch. So depending on the material that's chosen, you then have to consider, is the process appropriate for the material? Compression molding, ultimately, if you've got large diameter parts, or you want to save money by going to tube stock, or you want to use thinner sheet stock that can be molded easier and better than extruded, then that's your choice as well. But the bottom line is, you're always going to have to match all that up. You got to start with your physical numbers, then you got to match it up with the process and see if it all makes sense. A couple of other examples, just so you have a clear idea of what I'm talking about here. PTFE, Teflon, is another material that can be a little bit misleading, because if you look at most of the specs on PTFE, you will see a range of specific gravity. Now, most people don't consider specific gravity a big deal, but in the case of the PTFE materials, it is a big deal, because it can make or break a material in certain applications. The specific gravity directly relates to the crystallinity of the material, and the crystallinity of a PTFE directly relates to physical properties, its dielectric properties, and more importantly, the amount of porosity that exists. All PTFE has porosity, but how much can you tolerate? So you will see this spread of specific gravity, and that's kind of the telltale indicator of how much room the processor has to play with to get you a finished product. If you have ever gone online and looked for different specs that relate to PTFE, military specs, AMS specs, all the different specs that are out there, even OEM specs, you'll see a huge variation in what the requirements are. There are some applications that require highly tensilized extruded rod, for instance. There's others that require annealed materials. There are others that require certain fillers be used at very specific percentages. So all of these things have to be taken into consideration when you're considering using a PTFE, or really any of the fluoropolymers. PCTFE is another material that has the ability to have dramatic variations in crystallinity, which can dramatically change how the material is going to perform in an application. The third one I would bring up, and it's one that comes up on a regular basis for us, is TriStar's composite materials. Our two bearing grade materials, our UltraComp and our CJ materials, are really prone to a lot of questions, because we tend to be a little conservative on our numbers, and for some very specific reasons. If you look at the UltraComp, UC200 is our graphite composite, and the number that you'll see at the top of the list is our compressive strength, 54,500 psi. When you see a compressive strength number, whether it's a composite or any plastic, that is generally going to be its compressive strength at its extreme condition. That's the point at which it basically will self-destruct. You don't want to design a bearing around its self-destruct point. So the compressive strength data, whether it's on the UltraComp or the CJ or any other material, is really telling you this is the point at which that material is going to explode. So you don't want to design there. The other number that you'll see sometimes is the compressive strength to yield. The yield point is the point at which the material begins to change and lose some of its ability to recover. That's really not a point, especially if you're talking about a bearing application. It's not the point that you want to design around either. You could call that your top end number, but that's the limit that you would ever consider if you want to have a material that's going to be able to recover on a regular basis. So when we design with the UltraComp material, we're always going to design around reality, and the reality is 9 to 12,000 psi. That's a long way from 54,000. So that's why it can get a little confusing, is that the numbers don't necessarily translate directly to the application. CJs, same situation. Some of our competitors say that their compressive strength is 60,000 and 70,000 psi. That's great. That's no problem at all, but that's in a static condition. These are all static numbers. Why would you want a material that has a high compressive strength in a static condition when you're designing a dynamic bearing? It makes no sense whatsoever. So the better number to work with really is the PV value. What is the PV rating of that material? And then you got to look at the P, which if you've looked at it or watched any of our bearing videos, you realize that the P is the maximum static PSI the material can carry. And then you have the V, which is the velocity in surface feet per minute, and then that combined number will give you what the real capability of that material is. So whenever you look at physical properties on data sheets, remember to use those for comparison only. They're not really designed to be used for direct application design work. There's so many other parameters that you have to worry about when you're looking at plastics. As I've mentioned in other videos, the biggest killer of a plastic part is heat. And the heat is going to directly relate to the physical properties. If you've got a material that has a heat deflection temperature of 400 degrees, you don't want to design that material around 600 degrees, even though it may officially work at that temperature, but you've got to design around the reality of what the material is how the material is going to react. So temperature, loads, speeds if it's a bearing, what's the environment it's got to operate in, what's the hardware considerations, whether it's a structural part or a bearing part or a seal even, a gasket. All these things have to be looked at individually, and we would again encourage you to contact TriStar Engineering, and we can help walk you through this wasteland of information and give you some good direction as to which materials are really compatible with your application. Let us save you some of the hard work. We appreciate you watching, and hope this has been of some value to you. Don't be afraid. It's a big, ugly mess out there when it comes to physical data. When you're looking at plastics, there's thousands of materials and thousands of different ways to compound those materials and different blending technique. I mean, there's all kinds of things that you can look at. But we've been at it for a while, and we're more than happy to help you make that selection. Again, we appreciate you watching, and if you haven't done so, be sure and sign up for our blog site. We put out a lot of very interesting information, bits of information on applications, on materials, and we've gotten very high comments on the quality of the blog site. And I would also say I appreciate folks coming up to me when they recognize me from the videos and actually being complimentary about the things that we talk about. It makes me feel good about what we're doing here with our TriStar video library. So thanks very much, and I look forward to seeing you on the next TriStar videos. Thanks.